Okay, let's begin.
Devil on my shoulder is tempting me to be very controversial here, but I shall resist. Just gonna strike this out and write all, and everyone's gonna freak out. It's fine. Not many people watch the videos. It's not gonna go viral. It's okay. It's not like tomorrow you're gonna see me on a tablet. Jhevon believes all lives matter. Is not with us. Where were we last time? Yeah, there were two new approximation methods that we spoke about. There was the trapezoid method, trapezoid rule. That was the idea that says you want to find the area under some function on an interval, finite length AB. The idea was you created a bunch of, wherever the subintervals hit the curve, connected them with straight line segments, and you created trapezoids. So you find the area of these trapezoids and use that to approximate the area under the curve. And another new one was Simpsons Rule. You had a curve on A, B, and the idea was here you would take 3 points at a time. Notice that you will cover 2 subintervals in doing this, and then you just draw a parabola that goes through these guys. You do the next 3 points at a time, and then you draw another parabola that goes through these points. And then you find the area under these parabolas over the subintervals. And that will give you an approximation for the area under the curve. So let's talk about how we go about measuring areas using these two methods. Then we'll give some examples, and then we'll just move on. So let's talk about trapezoid. So if you have a trapezoid, right? So let's say the length here is going to be delta x. Let's say the height here is going to be y1. The height here is y2. How do you measure the area of this trapezoid?
Half base, y1, y2.
It's half the base times
y1 times y2.
it's the sum of the two, y1 plus y2. Right? So that's how you find the area of a single trapezoid. So it's 1/2 times the sum of the two parallel sides times the distance between them. Okay, so now you kind of put this together multiple times, actually. Right, so you can imagine that we have a scenario where we have a bunch of these trapezoids. Boom, 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 boom. Right? So let's say this is where your y1, your y2, your y3, your y4, your y5, etc. Notice that the area of this one is going to be delta x over 2 times y1 plus y2, whereas this one is going to be delta x over 2 times y2 plus y3. This one is going to be delta x over 2 times y3 plus y4. And dot, 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 etc. Up until the last one here is going to, but you can pretend it extends much longer. You would have delta x over 2 times yn minus 1 plus yn. That would be the very last guy. Right? Now, you just add up all these areas. That's what we're going to do. So that's the area of the first trapezoid, plus the area of the second, plus the area of the third, plus the area of the fourth, so on and so forth. And what you kind of end up with is the trapezoid approximation, with n subintervals, ends up being delta x over 2, which is a common factor in all of these. And notice now that you have your y1, which we can think of as f of x1, plus y2s, you're going to have 2 of those. You're also going to have 2 y3s. You're also going to have 2 y4s, etc. You're going to have everyone doubling up in the middle, all the way up to your yn minus 1, and then you're just going to have a yn. So it's going to be 2 times f of x2 plus 2 times f of x3 plus, and it continues like that until you end up with 2 times f of xn minus 1 plus your f of xn. And if you look at the handout that I gave you last time, there's that formula. So the trapezoid rule approximation for the integral from a to b of f of x dx is delta x over 2 times blah, blah, blah. That's where these guys come from. So it's going to be set up in the following way. Normally they start at x0. They start at the other endpoint. X0, x1, x2. But anyway, you kind of see where this pattern actually comes from. The first endpoint of the y value, this is literally where your a is. You're going to plug that into your function. That's going to be the first y coordinate. Where your b is, you're going to plug that into the function. That's going to be the last one. Now, for all the other subintervals, you double up in the interim, right? And then once multiplied by delta x over 2, that is equivalent to you adding up the areas of all the trapezoids. And that's where that formula comes from. So that's the trapezoid rule. So first and last y values stay the same. Double all intermediate y values. Multiply that by delta x over 2. That's your approximation using the trapezoid rule. Now the Simpsons rule is a little bit more complicated than that. Now for Simpsons, we're going to need to know how to find the area under a parabola. So let's look at Simpsons. So first, let me show you how to actually do it. Let's say this is some random parabola here on the interval, where this would be your delta x. That's going to be your delta x. But from now on, I'm going to call it h because it's easier to write than delta x. Here's going to be your x0, your x1, your x2. Here's going to be your y0. This is going to be your y1. This height is going to be your y2, right? That's your f of x0, your f of x1, your f of x2. Okay. We want to be able to find the area under this thing. Now, the idea is I'm going to figure out a formula by centering this at the origin. So that's the origin. But the idea is if I know how to find the area under this, I can just slide it along the axes and I'd be able to find the area under technically any parabola that looks like this. So here's what we're going to do. Let p of x equals ax squared plus bx plus c be the parabola. Then the area under the parabola, the area under this guy, is going to be the integral from minus h to h of that function. Now that's going to be ax cubed over 3 plus bx squared over 2 plus cx between minus h and h. And that's going to be, you're going to plug in h cubed, you're going to minus, when you plug in negative h cubed, that's going to become a plus. So you're going to get 2ah cubed. You plug in bh squared, then you're going to minus bh squared, so the middle term is going to cancel. Then you're going to get c times h minus c times negative h, so that's going to be a plus 2ch. So the area looks like that. Now let's actually do something with that expression. Well, I'll come back to it right here. Now, let's actually make sense of that. Something that we can apply in general, sort of like this. What we can do is to start finding values that we can rewrite the A and the C in terms of any X or Y coordinate, or in terms of those X and Y coordinates. Here are some things to notice. If I take P of H, notice that that gives me Y2, right? So this is where X equals H, the output is Y2, but P of H is also going to be AH squared plus BH plus C. Notice that if I take P of minus H, that's P at this coordinate, that's going to be your Y0, and that will be AH squared minus BH plus C. You can notice that I could add these two, and I would get Y0 plus Y2 is going to be equal to 2AH squared plus 2C. So now, remember that, we're going to use that later. Another thing that we can note from this parabola is that P of x1 is just going to be, well, P of 0, essentially, which is going to be y1. But that, if I plug into the original formula, is just C. So I also know that my y1 is C. What are we going to do with that? Well, now, using these two, we're going to go back up there. I want to take advantage of that expression, the 2AH squared. Here, I have 2AH cubed over 3. So what do? Let's factor out 2H over 3. Or let's factor out H over 3. So I'd be left with 2AH squared right here. Plus, if I factor out H over 3, I'd be left over with 6C. So this is 2AH squared. The 6C, I'm going to break it up into 2C. Plus 4C. Now, this expression here, I know is my y0 plus y2. And since my C is y1, this expression over here is 4y1. So in other words, this entire expression is h over 3 times, well, y0 plus 4y1 plus y2. That's it. Okay. In other words, if you want to make this look more like our common notation, basically I'm saying delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. So now what we're going to do, we're going to put these guys together. So you can imagine you have this graph doing its thing. So now you look at the area under this parabola. Let this guy be your x0, your x1, etc., your x2, x3, x4, x5, etc. Notice that the first part is going to give us an area of delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. And then you would create a second parabola, which is going to cover the next two intervals over here. Now the area of that one is going to be, well, delta x over 3 times f of x2 plus 4 f of x3 plus f of x4. and so on, right? So this pattern is going to continue until you end up with like the last guy, which is going to be delta x over 3 times f of xn minus 2 plus 4 f of xn minus 1 plus f of xn. And you're going to add up all these guys together. Dot, dot, dot. Right? So now, when you put them all together, you end up with the Simpsons approximation from n subintervals. Delta x over 3 ends up being your common term. So we can factor that out, put it all in front. Notice how we start off with these guys. F of x0 plus 4 f of x1 plus. Now look at what's happening to your x2. Your x2 gets doubled up from the last guy in this set of parentheses. He gets added to the first guy within those set of parentheses, and that gives us here 2 f of x2. Now it continues with 4 f of x3 plus. Now this f of x4 is going to double up with the first guy in the next set of parentheses, which is another f of x4, so you're going to get a 2 f of x4 plus dot dot dot. So notice you're going to get this pattern. Your first y value is just whatever the y value is, but then you start taking 4, then 2, then 4, then 2. You alternate 4s and 2s, going all the way until you get to dot dot dot, the end. This guy's going to double up with the last guy from the previous set of parentheses, so I'm going to have 2 f of xn minus 2 plus 4 f of xn minus 1 plus f of xn. And look at the formula for Simpsons Rule. That's what you see here in the pattern. So it starts with delta x over 3. The first y value, nothing changes, but you start multiplying y values by 4, then 2, then 4, then 2. So you alternate with 4 and 2s, starting with the 4. Because the 4 comes from, well, that's where it comes from, right? The middle term starting with the first guy is going to be the 4. Then it doubles up, then it goes to a 4. Then it doubles up, then it goes to a 4, and so on and so forth. So 4, 2, 4, 2, 4, 2, 4, 2. And that's where this formula comes from. Another thing that's peculiar to Simpsons Rule is that one thing you want to notice is that for a single parabola, he takes up 2 subintervals. Right? So a single parabola is 3 points. These 3 points span 2 subintervals, which means in order to be able to span something with a bunch of parabolas, I will need an even number of subintervals. So that's going to be something that's strange. So for Simpsons Rule, you must have an even number of subintervals, right? Because I need 2 subintervals for each parabola that I'm setting up. The other ones, they don't really care how many subintervals you use, but Simpsons Rule in particular needs them 2 at a time. So that ends up being there. So that's where these formulas come from. Now, of course, the midpoint rule, the right-hand rule, the left-hand rule, you learned that from Cal 1, not going to go over that. I'm going to assume you know how to do with that. Also assume you know things like delta x is b minus a over n. That's also something you got from part 1. Then we're going to move over to the next section. Now, this is something I just want to talk about briefly, not going to drive any of it because I'm not required to go in depth with it for the syllabus, but it's an important idea to understand because an approximation is only as good as you know how good the approximation is, right? So these guys are formulas that actually tell us the errors that we obtain by using these approximations from around here. So the first one that says the error in the midpoint rule, that's E sub n, it says that that error is going to be bounded by this guy, which means these expressions here tell you how wrong you could possibly be by using one of these methods. So I have error estimations for the midpoint rule, for the trapezoid rule, and for the Simpsons rule. It's very important to know that this k value here, and we'll actually do some examples for the k, the k value here is going to be chosen by the reader. It is going to be a number such that for the midpoint rule and the trapezoid rule, the magnitude of the second derivative must always be less than or equal to that number on the interval. For the Simpsons rule, you need up to 4 derivatives. The magnitude of the fourth derivative must be less than or equal to that number on the interval. So we're going to do some things like that. I'm going to show you how to calculate, not only approximate integrals with these methods, but also how to estimate the errors that you would have. How far would you be from the actual answer if you were to use these methods? That's going to be something that's good, and I'll kind of explain as we do it how you might apply something like that. But yeah, let's actually jump into the examples on the handout.
Jhevon,
Yes.
before you erase that, where did our b disappear?
Coming in?
The b term, where did that disappear to?
Oh, but I use the fundamental theorem of calculus. So I plug in the top. That would give me AH cubed over 3 plus BH squared over 2 plus CH minus, plug in the bottom. Now if I plug in a minus H into a cubed, it becomes minus. If I plug in a minus H into a square, it doesn't do anything. And if I plug in the minus into the X, it becomes minus CH. So what ends up happening, you end up with this guy, this guy subtract that guy, but you have this guy minus a negative that guy, so that guy doubles up to 2. And then I have CH minus a negative CH, so then I get 2CH. So the b's cancel because of the square actually made the sign change. Cancel each other out. So, important thing for trapezoid rule, because you have to have these formulas memorized, I'm not going to give them to you. The only thing that I would give to you for a quiz, I suppose, I probably won't test you on it, but for the quiz, I'm going to test you on errors, and I'll give you the formulas for the errors. But of course, you're going to have to know how to use them. Right. But we're going to cover all of that. So, now I'm going to modify these examples a little bit. Because again, we have limited real estate here. Your textbook really focuses on the Simpsons rule and the trapezoid rule in this section. It already covered left and right and midpoint in a previous section where you were learning about like Riemann sums and that sort of stuff. So I want to really focus on the Simpsons rule and trapezoid rule also. So we're going to ignore all the examples that ask about midpoint rule and just kind of do everything for Simpsons and trapezoid. As well as to make something also a little bit more interesting, I'll probably change that thing from a sin x to something else, maybe like a sin 2x or something like that.
Same interval?
But same interval, yeah. So let's do example 1. Here's what we're going to approximate. 0 to pi of the sine of 2x. Not sure if 3x would be more interesting. Maybe 3x. I think I've done 2x before. Let's spice it up. Okay, so we're going to use n equals 4. And I want to do a Simpsons approximation, and a trapezoid approximation, and a Simpsons approximation. And then I'm going to want to measure the errors that will be associated with each of these approximations. So, yes, I know you can actually integrate that and actually find the exact error, but the exact area, but I just want to get you used to using these rules without making the function too complicated. Okay, so, hey. So, let's run through this quickly. We're using the trapezoid rule approximation. Now, whenever you want to use any one of these approximations, the first thing you're going to want to find is your delta x. Your delta x is b minus a over n, which in this case is going to be pi minus 0 over 4. So that's the first thing, find your delta x. Second thing you're going to want to do is you're going to find the xi. Now you kind of already know a formula to find the xi, it's a plus I delta x. I like to actually just sketch out a little picture on the spot though. So 0 to pi, I realize I want to cut it into 4 equal sections, and I know I start at the first endpoint and I keep adding delta x. I'm going to add pi over 4. So I'm going to pi over 4. I'm going to add pi over 4 again. That gives me 2 pi over 4. I'm going to add pi over 4 again. That gives me 3 pi over 4. Add pi over 4 again. That gives me 4 pi over 4, which is the last guy. So I keep adding pi over 4. So those are my xi's. So this guy here is my x0. This guy here is my x1. This guy here is my x2. This guy here is my x3. And the last guy here is my x4. Now, once you find your delta x and you know the xi's, you're just going to plug into the formula for that. So the trapezoid approximation with 4 subintervals is going to look like our area is approximately equal to T4, which is delta x over 2 times f of 0 plus 2 times f of pi over 4 plus 2 times f of pi over 2 plus 2 times f of 3 pi over 4 plus f of pi. So that's what the formula is going to look like. And now it's just plug and chug. Coming from integrals and improper integrals, this is actually not going to, conceptually, shouldn't be, at least, too crazy to wrap your head around. Delta x is your pi over 4, so you divide that by 2, get pi over 8. F of 0, so this is going to be sine of 0 plus 2 times sine of 3 pi over 4 plus 2 times sine of 3 pi over 2 plus 2 times sine of 9 pi over 4 plus sine of pi. Now I do expect you to know what these guys are. Sine of 0. 0. Sine of 3 pi over 4. Huh?
Negative root 2 over 2.
Root 2 over 2. Plus sine of 3 pi over 2. 0. No.
All negative 1.
Sine of 9 pi over 4.
Yeah, negative root 2 over 2.
Is it negative? What quadrant is 9 pi over 4 in?
The third. Oh, wait,
I thought the rotation was plus a pi.
it's just 5 2 over 2.
It's root 2 over 2. 9 pi over 4 is in the first quadrant.
Yeah.
Right? Take a circle, divide it into pi over 4 pieces. One full revolution is 8 pi over 4. 9 pi over 4 is 1 more. You're in the first quadrant. Okay, so sine of pi. Okay, so what we have, well, this cancels that. So we have pi over 8 times, well, root 2 minus 2. Or, I mean, it doesn't matter, I'm fine with that actually. But you could write this as something like, say, pi over 4 times root 2 minus 1. That can be your approximation for the area under this curve. So the integral from 0 to pi of sine of 3x is roughly, well, if I approximate it with trapezoids, using 4 trapezoids, it's going to be roughly that area. And that's basically it. So you're going to find your delta x, which is b minus a over n. You're going to find your xi. You can draw it out if you want. I like drawing it out. So you start at the a, then you keep adding delta x until you get to the last guy, and then you plug into the required formula. So for the trapezoid rule, the first and the last y values stay the same, but you double up all intermediate y values, multiply by delta x over 2, and yeah, now it's just a plug and chug. Actually do the computations and just simplify. Now, in general, you don't need to like, and I'll usually put instructions saying this. Sometimes if it's not something that it's nice to simplify, it'll just be like a sum of these really ugly looking numbers. You can just leave it as a sum of numbers as your answer, and you would like box this whole thing, and that would be your answer. But if it's easy to simplify, just simplify it. But if it's going to be complicated, I'll leave instructions that say, oh, you don't have to combine anything, just leave it as a sum. I just want to know that you know how to do these 3 phases. Right? So this would be an approximation, how we can approximate that integral using 4 trapezoids. Questions? Let's do B, which B is going to start out exactly the same way actually, but let's just go over it again. Making sure that everyone actually catches it. So B. What would Simpsons Rule say the area is with 4 subintervals? Well, again, first thing you want to do is you want to find your delta x. This is b minus a over n pi minus 0 over 4. Right? That will always be given. We'll tell you, oh, use 4 subintervals or n equals 4 or something. That will be indicated. Start with 4. 2, you're going to find your xi. So that's 0. Pi, you know you want 4 sections. Keep adding pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So those are your xi. Third, you're going to plug into the formula. Now for Simpsons, using S sub n, well in this case S sub 4, that is going to be delta x over 3 times. Now it's f of 0 plus, well plus what? 4
Sine.
f of
That's pi.
plus
2 pi.
2 f of pi over 2 plus
4 f pi. 3 pi over 4.
That's f of pi. So it starts at 4 on the second y value and alternates between 2. So it'll start at 4, the last alternation ends on a 4. So that's kind of your pattern here. So it starts at a 4, ends on a 4, starting from the second to last y values. Okay, so now delta x over 3, that was pi over 4 over 3, so this is pi over 12. And I'm going to do sine of 0 plus 4 sine of 3 pi over 4 plus 2 sine of 3 pi over 2 plus 4 sine of 9 pi over 4 plus sine pi. So sine of 0 is 0. Sine of this is 3 pi over 4. That is in the second quadrant. Sine is positive. 3 pi over 2, your sine is minus 1. 9 pi over 4, that's in the first quadrant, so it's positive. Sine of pi is 0. Then that cancels into that. That cancels into that. So I have 4 radical 2 minus 2. So, in other words, the Simpsons approximation is going to be pi over 6 times 2 rad 2 minus 1. That's this approximation. Yeah, I'm only going to ask you about Simpsons Rule and Trapezoid Rule, but all the approximation methods that we have listed here go through this kind of technique. Start out by finding your delta x, find all your xi, then plug into the formula that's on the page. You will be expected to memorize this thing. So you have to remember that for the Trapezoid Rule and the Simpsons Rule. Notice that the Simpsons alternates starting with a 4 at the second y value. And it needs an even number of subintervals, things like that you should know. While the Trapezoid Rule just doubles up all the intermediate y values. But these would be our approximations for the interval. Now, let's talk about errors. Find the errors in the approximations. In 1, So now, the error formulas I'm going to give you, so you don't have to memorize those. If I ever ask you about errors, I'll give you the formulas to use. So, we care about the error for the trapezoid rule, that's your E sub t. We know that that's going to be less than or equal to big K is B minus A, that's to the cubed?
Yeah.
Over
12n squared.
12n squared. And here, where your second derivative of your function in magnitude is less than or equal to k on this integral. And of course, you do want your k to be larger than the second derivative, but you'll kind of strive to pick the smallest number you can think of that's largest on that integral. Because otherwise you're going to get like an overblown estimation for how wrong you are. And you kind of want to keep things a little bit tight. Versus we have an error associated with Simpsons Rule. And I believe it's b minus a to the 5th over, it's like 180 and so forth.
Yeah, 180.
Your k here has a larger requirement, quote unquote. The fourth derivative of your function needs to be less than or equal to k on AB, where again, your k, the chosen k should be minimum. You want it larger than these, the magnitude of the derivative, but you want the smallest guy larger than it. So those are the error approximations. So this basically tells you when you do a trapezoid approximation with n subintervals, how far from the actual answer should you expect to be? Well, you should be within this expression of the actual answer. So let's actually see in the previous section, with f of x equals sine of 3x and n equals 4, what is the errors? Like how far is this from the actual answer? And how far was our first thing from the actual answer? So, what I want to do now is I want to be able to approximate what my k value is going to be. My b and my a, I know what those are. Those are just endpoints on the interval. My n, I know what that is. That's the number of subintervals I'm using. I just want to now know the k. So, let's start with my f of x. What is f prime?
3 cosine 3x.
At double prime.
Negative 9 sine 3x.
Triple prime. Oh, this is A was trapezoid.
Yeah.
So we only need 2 derivatives. So this means we want the magnitude of minus 9 sine 3x to be less than or equal to k on the interval 0 to pi. Can you tell me a nice k to choose? 9. Choose k equals 9. Because my sine function is going to be less than 1 in absolute value, so 9 times that in absolute value should be less than or equal to 9. So I'm not going to like say k equals 1,000, even though it's true. That's just going to overblow my error estimation. So I would choose k equals 9. So my error associated with the trapezoid rule should be less than 9 times pi minus 0 cubed over 12 times 4 squared. So that's going to be, well, this goes 3 through that goes 4. So that's going to be 3 pi cubed over 16 times 4, so that's 64. Alright, so that's the error. Just for fun, let's see what is that? As a decimal. Let's see. 3 times pi cubed divided by 64.
It's like 3 over 2.
Huh?
What is it, like around 3 over 2?
Yep. It's around 1.453. So far off. I mean, it's a sine function, like very wavy. Trapezoid probably isn't going to do it justice. Maybe a Simpsons approximation would be better. But that's how far I can expect to be from the actual answer. So my approximation with the trapezoid rule in this case is going to be whatever the actual value is, plus or minus 1.5-ish. Right? It's going to be about 1.5 units, square units off. Let's look at the error for Simpsons. Yes?
Wait, why did you choose 9 for k again?
Because the requirement is I have to be, the magnitude of the second derivative, as we found here, must be less than or equal to k. And the smallest thing I can think of that's greater than or equal to that is the number 9. Because the sign is less than or equal to 1 in absolute value. So yeah, let's see if Simpsons is any better here. So for Simpsons, we need 4 derivatives. We need to check this requirement with the 4th derivative. So 2b. F prime is going to be 3 cosine 3x. F double prime. Triple prime. Is 81 sine 3x. And so here we want the magnitude of the 4th derivative, which is the magnitude of 81 sine 3x, to be less than or equal to k on 0 pi. A safe k value to choose. Choose k equals 81. Then the error that we found earlier, in the approximation that we found earlier, should be something less than 81 times pi minus 0 to the 5th over 180 times 4 cubed. That was a cube, right? So,
Before
huh?
Instead of
Cube.
So let's actually see what that is roughly. This is A1 pi to the 5th over I'm going to use decimal so it doesn't matter. So 81 times pi to the fifth divided by 180 times 4 to the fourth. Now, as expected, well, this one's off by 0.538. So the Simpsons here actually gets closer, which makes sense. It's a trig function. It's very wavy. It kind of looks like a parabola. The parabola would obviously be the better method to choose here. So, some things to consider. We're doing approximations. Why? Was this very difficult to find the area under the curve? No, it's just that in general, sometimes we have integrals where we'd like to be able to compute them, but we can't. So, for example, if I wanted to approximate, or if I wanted to compute this integral, I couldn't actually do it, right? Because I don't know how to find the antiderivative of that guy. So what we could do instead is we can use an approximation method, which now you know a lot of them. You know, like 5 methods at this point. So basically what you would do is you would use an approximation and you would have a tolerance of what you would want to be within. So you're like, okay, I just want to be within 5 decimal places of the actual answer. So what you can do is then you would actually check with this error approximation how close you are to the answer, and then you can use more subintervals if you want. In fact, with these error approximations, you could actually estimate how many, you can actually know what n value you need. Let's actually do that. Let's follow up. So for this same function, suppose I wanted suppose let's say to 2 decimal places, just for fun, to within 1/100th of the actual answer. Using Simpsons. How many subintervals do you try? Now, once I tell you the subintervals, you know how to actually get to the answer using that number of subintervals. So, if I didn't give you the number of subintervals, how would you actually pick how many do you actually need? Well, with a question like this, I want to approximate, so again, remember, we want to approximate 0 to pi of the sine of 3x dx, right? Let's say I've chosen, you know what, it's very wavy. The guy that's going to give me the closest answer with the least number of subintervals is probably going to be Simpsons Rule, because using rectangles or trapezoids just doesn't make sense to me in this context. So I'm going to use Simpsons. However, I also want to, being off by 0.5 square units is way too much. I want to be off, I want to be correct. I want my error to be like 0.001, right? Or 0.01, that is. Right? How many subintervals will we actually need? Using 4 subintervals, that's my error. What does n need to be to get the error to be this? It turns out, in this case, what you would do is you would start off with the error approximation. So we saw k was equal to 81 for ES here. Right? So we need to choose a number that is larger than the 4th derivative on the interval of consideration. 81 was the right number. Now, suppose we didn't know n. So we know our error estimate is going to be within How do I know what n I would have to pick to get that to be the right thing?
Algebra.
Yeah, but what am I solving for with the algebra? Yeah,
And just make them cancel out,
make what cancel out?
as in make and some constant multiplied by pi times pi over 4. Cancel out like Simpsons, you get over 100.
How do you guarantee that you'll get that when all the cancellation happens? Well, the easiest thing to do would be to set this equal less than that, right? If the error is bounded above by that, just make sure it's bounded above by the error that I want. So you're going to set up this inequality. And you're essentially solve for the n that makes that inequality true.
What if you didn't have a previously chosen k?
Well, you'd find it. You'd actually, this thing, take a bunch of derivatives, right? Taking derivatives is not hard, right? Like, taking integrals is what's hard, right? So I can't integrate that, but if I want to approximate that within a certain thing, within a certain tolerance, I can just take 4 derivatives and set up this thing, see what that's bounded above by the 4th derivative. And yeah, so I would set up this inequality, and now I'm just gonna actually solve for n. So here, notice that you can flip both sides of this. You get 180 n to the 4th over 81 pi to the 5th. Must be greater than or equal to 100. And so you would get your n to be greater than or equal to 100 times 81 pi to the 5th over 180, and then all of that to the 4th root. And of course, to be kind of accurate, you do something like a ceiling function of this, meaning round up to the next integer. This is a decimal. So that would give us roughly what? So you can go ahead and kind of know how many subintervals you would need here. Now, of course, on a test, that would be your answer. You'd write this down, but I'm just using the calculator just for out of curiosity to see roughly how many n's we would need. It's actually not that a lot. This is around 10.8. So this is around 11, but for Simpsons, you bump it up to 12. Because Simpsons needs an even number, right? So you'd say, okay, choose n to be the next even integer larger than that. You'd only need 12, which is not a lot, all things considered. In general, functions are complicated that you'd actually want to use hundreds or thousands of subintervals, but for this, to get that tolerance, you only need 12. Interesting. Okay, that's all I want to do. You can try problems 3 and 4. I would, instead of using midpoint approximation, try Simpsons and Trapezoid with problem 4, and yeah, that'll put you, give you some good practice for the quiz.
Jhevon,
Yes.
quick question. If the n we came out with was even to begin with, would we still need to go 1 higher or 2 higher or whatever?
No, you just leave
We'll
it.
just use that one?
Yeah. So for Simpsons rule, using 11 doesn't make sense. It has to be
Yeah,
a
it has to
number.
be.
So you don't want to go lower because that's actually worse. So you just bump it up to the next one higher. And that's that. So that's approximate integrals in a nutshell. That's all you need to know for this section. Actually, it's probably a little more than you would need. Technically, you don't have to know about errors, but I think it's a very important thing to consider. Like if you're using an approximation, you should kind of consider how good it is. How wrong can I be? You always want to know that, how wrong you can be. It's always very important. Everyone's concerned with being right all the time. Sometimes you need to know. You need to hedge your bets. You need to know, how wrong could I possibly be? What are the chances that I'm wrong in this opinion? Always good to know. So I'll quiz you on this for sure. I might not put it on test though, because there will be many other things to test you on by the time test 1 comes around. But so next week I'm going to ask you to approximate things with Simpsons Rule, approximate things with Trapezoid Rule, as well as use the error formulas. And what did we do on Monday? So on Monday we did, I don't know if I'll test you more on improper integrals, but okay, so that's it. That's it for this topic. We're going to move on to another topic. At least we're going to introduce it. And you're going to start talking about sequences and series, but we're going to start it with point 1, sequences. So we're moving into the next phase. We did a lot with integration in the first part of the class. Now we're going into the second phase of the class, which is the series section. But we want to start this discussion with sequences. Not going to be super comprehensive here. Just going to tell you the basics about sequences. But for the most part, what we want to know about sequences is what's going to help us with series, actually. So the main goal is to talk about series, but we want to use a sequences perspective here. So let's start talking about sequences. I'll give you some of the basics here, what we especially need to know about sequences that are going to help us with series. So let's begin. Let's start with the definition. What is a sequence? A sequence is a list. For us, it's a list of numbers. In general, it can be a list of anything. But it's a list in a definite order. Right? So you can think of a sequence as an ordered list. There's a list of things, but there's a notion of who's the first guy in the list, the second guy in the list, the third guy in the list, and so on and so forth. So that's all a sequence is. It's basically a list in a definite order. So, for example, I can talk about this kind of sequence. List. So here's a list of 4 things. It's a list in a definite order. I definitely had in my mind what would be first, second, third, and fourth. There was some kind of rule I was following in my head to actually write this list down. Another example would be something like dot, dot, dot. Okay. So these are 2 lists. Mathematically, we would call them sequences. These are 2 sequences. This one here, this, as you notice, the list terminated. There was a last guy. This is called a finite sequence. This guy, we write ellipses. This indicates the pattern continues. So this is called an infinite sequence. It's just a list that goes on forever. Now there is a definite sense of order. There is a rule that I was following that tells me who should I write down first, second, third, fourth, etc. But the pattern just continues. I keep doing this forever in theory, and I can generate that list. Another thing that you want to be aware of is that we can name sequences, like we can name functions. Well, actually, exactly like we can name functions. Another way to think of sequences is as functions, and I'll talk about that as well. Another way to think of a sequence is thinking of it as a function. Like how we can name functions, we can name sequences. So example, I can talk about a sequence A sub n, okay, and we write it like that. Now you can also put indices on this, so I can have a lower index or a lower limit, saying n goes from 1 up to 4. So this tells you here's a sequence, it's 4 items long. It starts at the first guy, then the second, then the third, then the fourth guy. So this I could think of as A1, A2, A3, and A4. These guys are called the terms of the sequence, by the way, the individual guys. Together they're called the terms of the sequence. That's the first term, the second term, the third term, etc. And so this is the starting point. And this is the ending point. Now I can represent an infinite sequence in this case by just actually writing an infinity in the upper bound. For example, I could write n goes from 1 to infinity, and this is an infinite sequence. So we can name them like a sub n. You usually name them with a lowercase letter and a subscript. So, mention that. So the subscript tells you where in the list you are. So the subscript of 1 tells you I'm looking at the first guy in the list. The subscript of 3 tells you I'm looking at the third guy in the list. So in example 1 above, I could say an, or let's call it bn, and goes from 1 to 4, is defined by. So we can also talk about a formula that will generate people in our list. So if I was thinking about a definite order, maybe I might have a formula or a way of coming up with these numbers. So I can, what is the rule here? How was I coming up with that list?
What, plus the first one?
Add 4, right. So I start with -1 and I want to add 4. So I can write that as a formula in terms of n. So I can say, here's a sequence, it's 4 items long. Here's a formula for how you generate the members of this sequence. I can start at, say, -5 and keep adding 4n. So the first guy is going to be -5 plus 4 times 1. The second guy is -5 plus 4 times 2. The third guy is -5 plus 4 times 3, etc. That will generate the members of that list. Now for the second list, who knows what that is?
Fibonacci.
That's the Fibonacci sequence. Very important sequence. A lot of people like it. It's one of those things that people geek out on all the time. You know, like those people geek out on pi all the time. And chances are, if you see one of those dudes who are like, I can prove God exists through math. He's going to talk about the Fibonacci sequence at some point.
That dude outside the net.
Like there are a lot of things in our neck of the universe that follow the Fibonacci sequence. Fibonacci himself came up with it by studying rabbit populations of all things. So in example 2, this is the Fibonacci sequence. Now its definition is what we would call a recursive definition. So, I mean, there is a way to find a close formula for it, but we're not going to worry about that. So we can say, now this is one where it's special. So they usually use an uppercase letter for that sequence, but whatever. So it says how it would be defined is they'll tell you who the first guy is specifically. So they'll say the first member is 0. Then they'll say the second member is 1. And then they'll say something like, all new members are generated by adding the 2 previous members. So it's going to be fn minus 1 plus fn minus 2 for n greater than or equal to 3. So it's saying, to find f3, you're going to add f2 and f1. Then to find f4, you're going to add f3 and f2. Then to find f5, you're going to add f4 and f3, and so on and so forth. So it starts with 0 and 1. So f1 is 0, f2 is 1, f3 is going to be 0 plus 1, which is 1, f4 is going to be 1 plus 1, which is 2, f5 is going to be 2 plus 1, which is 3, and so on. So this kind of definition is a very special kind of definition. It's called a recursive definition. This is called a recursive definition. So any definition that depends on you knowing a few guys to start off and then all new guys are defined in terms of previous guys, that's called a recursive definition. Remember, that shows up. So the Fibonacci sequence, the most popular way to define it is in terms of this recursive definition. You start off with 2 guys and just say, generate all new guys by adding the 2 previous guys. And oddly enough, that actually can generate a lot of patterns that we see in physical reality, and it's connected to the golden ratio and all this really cool stuff. Anyway, moving on. So sequence is a list in a definite order, and we can name them, and we can define them via formulas, or via recursive definitions, or pretty much via any rule that you can define a function with. So let's actually talk about sequences as functions. So another way to think of sequences are, think of them as functions. Functions with a particular domain, whose domain is the positive integers. Some people start at the non-negative integers. They start at the 0th term in the first term, but we'll start at the positive integers. Right? So, in other words, I can think of the Fibonacci sequence as just a function. The function takes 1, which is the first positive integer, maps it to 0. Takes 2, maps it to 1. Takes 3, maps it to 1. Takes 4, maps it to 2. Takes 5, maps it to 3. Takes 6, maps it to 5, etc. Right? So it's defining a function in which f of 1 is 0, f of 2 is 1, f of 3 is 1, f of 4 is 2, etc. Right? So I can actually think of it as a function that the domain is always the integers. So you can even think of the domain as being the subscripts of the members of your list. So you connect the subscript to the number, which you can think of it as the output. So this is the subscript, and that's the actual value of the term. Now, when you think of it that way, a lot of things can make sense, because once you can think of it as a function, now you can do things like graph it on an XY plane. You can talk about how a sequence would behave and the trend of a sequence and so on and so forth. Which is what we're going to move into now. So, when it comes to sequences, the most important thing that you need to remember about a sequence, and it's going to be very important for series as well, it's an idea talking about the convergence of a sequence. So, there is the idea of saying a sequence converges versus a sequence diverges. What does that mean? So, we say a sequence AN converges to a real number L if the limit as n approaches infinity of AN equals L. So that's it. Find a way to express this guy as some sort of formula or function or rule, and then take the limit as you approach infinity. What do all the values of the terms approach? If they approach a real number, we say the sequence converges to that real number. And we may write limit of an equals L, or an approaches L in this case. If no such L exists, or L equals plus or minus infinity, we say the sequence diverges. So a sequence may converge or it may diverge. Converges means I can take the limit of the expression that defines the terms of the sequence. If it approaches a real number, I say the sequence converges to that number. And in that case, I can write this or that. And if there is no such number, I say the sequence diverges. Now, I want you to notice here, what I did was what up until now would be considered very bad form. I just wrote an LIM without telling you what is approaching what. And the reason why that's okay in this situation is because literally it is always n approaches infinity. It does not make sense to approach any other thing for a sequence. And if you actually think of it as a function, actually sketch it out, you'll see why that's the case. So I can be lazy and just write LIM when talking about sequences because it's understood that I'm talking about the limit at infinity. Now why is that? Let's see. Suppose, let's do some examples. I have an infinite sequence. It is defined by each term is given by this expression. Now I can ask, does this sequence converge? So, when you want to know a sequence converge, whether it converges or not, what you're going to do is you're going to take the limit of the sequence. Always what you do. So what we're going to do is we're going to take the limit of the sequence. Now, you will notice that if I took the limit of an and n approaches infinity is implied, and I'll talk about why that's implied, this just means the limit as n approaches infinity of 1 over n, which everyone would know at this point is 0. So I can say, yes, an converges to 0. Now, what would a picture for this look like? So, let's say I was sketching this out on a graph, and my n is here, and my out with my terms are over here. What would this guy actually look like? Well, 1 over n. So, remember, the inputs are just the integers, right? So 1, 2, 3, 4, 5, 6. The outputs are just going to be the values of this thing. So when n equals 1, you plug it in here, you get 1. That's that. When n equals 2, you plug it in there, you get a half. That's that. When n equals 3, you plug it in there, you get a third. That's that. Then when n equals 4, you plug it in there, you get a quarter, then you get a fifth, then you get a sixth, and so on and so forth. Now what you'll notice is that if someone were to ask about what is the limit as n approaches 2 or 3, right? As we approach 2, is that even possible? No. For limits to work out, you have to be able to get arbitrarily close. You have to be able to get inch closer to the left and inch closer to the right, but you can't do that. There's a gap. There's a gap. There will always be a gap between any two terms. So you can't actually take a limit approaching any intermediate number. You can't take a limit approaching 3. A limit doesn't work there. A limit has to be able to get close, but you'll never be able to get close to any one point. However, what you will be able to talk about is an overall trend, right? You can kind of see that these guys have this kind of trend. They're heading towards something. all the guys, if I think of them all as a group, they're all going towards something, and I can say, does this converge? And what I'm trying to say, is there a trend that goes to some meaningful value that I can ascertain? And in this case, the answer would be, yeah, if I kind of track all their outputs coming back to the y-axis, or the vertical axis, you'll notice that all the outputs are inching towards 0. So I can say the trend is they're all going towards 0. Or in other words, they converge to 0. Right? But I can only talk about convergence as we go off to infinity, because for any intermediate step, I can't actually approach any intermediate point. So, the sequence 1 over n converges to 0. We can do another example. N equals n. And I can say, does this converge? Well, I could think of this as a picture. Here's my an. So, my 1 would map to 1, my 2 would map to 2, my 3 maps to 3, my 4 maps to 4, my 5 maps to 5, and so on and so on. Right? So that would be what this picture starts to look like. You'll clearly see there's an upward trend. Where is that trend going towards? Well, it's going off towards infinity. You'll notice that the limit of an is going to be the limit of n. Well, that's just infinity. So I would be able to say here, an diverges. Now, you could say diverges to infinity, but in general, I'm not going to care if you tell me what something is divergent to. It could diverge to infinity or positive infinity or negative infinity. But if it diverges, it diverges. A divergent sequence is going to be useless to us. We care about when they converge to something. That's going to be meaningful in future sessions. So, that one diverges. The first one converges. Here's another example of a sequence. It involves a very important expression that we will be using moving on. So, defining an infinite sequence, it's given by this formula. -1 to the n. Right? So that's going to be a very common thing that we're going to be dealing with here. Notice how this guy looks, if I look at an here, what are the outputs? Who's the first guy? Well, it's going to be, plug in n equals 1, because it starts at 1, so you're going to get -1. Then you're plugging n equals 2, you get +1, n equals 3, minus, and plus, and minus, and plus, and minus. This generates an alternating sign, and that's how we're going to be thinking about alternating signs moving forward. It's just a function. It's just a sequence, -1 to the n. If I want to describe any alternating signs, I can describe it with a sequence, -1 to the n. Or something similar, -1 to the n plus 1, or something like that. If I want to start off at a positive 1, I might have said -n plus 1, or something like that. But here, this guy just jumps up and down between -1 and 1. And I might ask, does this converge? Right? Now, some of you already saw the answer is no, but if I were to draw a picture, what would actually happen here? Well, there will be two trends that are occurring simultaneously. There will be a trend of guys going towards 1. There will also be a trend of guys going towards -1. So at 1, it's at -1, and at 2, it's at +1, then -1, then +1, then -1, then +1, -1. And this guy just, the trend is just, we're bouncing up and down. Now, does that ever actually settle anywhere meaningful? Well, no, it'll always just keep bouncing up and down. The limit is not going to be 1, it's also not going to be minus 1. In fact, it's not even going to say, it's not even right to say the limit is infinity. The limit just does not exist. In this case, if I look at the limit of an, that's just limit minus 1 to the n, and this just does not exist. So I can say an diverges. Not to infinity, it just diverges. Like there's nothing else to say there. It doesn't settle anywhere. Okay? But that's a very important kind of expression. We're going to get back to that pretty soon. So those are the important things. A sequence is basically a list of things, a list in a definite order. We're going to think of it as a list of real numbers in general. But there's an order to it. We can write it down in a formula. I can express what it's doing as an equation. And we can think of it as a graph, but it's a graph of isolated points. So if we're taking limits, there can only be one limit that's worth taking. The limit as you go up to infinity to talk about the trend. And whenever we're asked about whether something converges, that's what you're doing. The convergence of a sequence is just take the limit of the sequence. Do you get a real number answer? If yes, it converges to that number. If no, it diverges. That being said, let's look at some properties. Because, of course, this involves limits, so you're going to have to remember all of your limit rules. So I'm going to expect you to remember your squeeze theorem and your L'Hopital's rules and all that good stuff. How limits work. Now, since this is kind of a new topic, let me just remind you of some basic limit rules that still actually work here. Properties of converging sequences. So an, bn are convergent sequences. C is a constant. Here are some facts. These are things that you can assume to be true whenever you're dealing with sequences and you're algebraically manipulating things. One, if you take the limit of a constant times a sequence, it is just a constant times the limit of the sequence. You can factor constants outside of limits for sequences. So that still works. That's good. The limit of the sum or difference of two sequences is actually the sum of the limits of the sequences. So limits still distribute across sums. 3. Limit of a product of sequences is the product of the limits of the sequences. So that's still true. That's nice. They also distribute across divisions. So if I have the limit of one sequence divided by another sequence, this is just the limit of the top sequence divided by the limit of the bottom sequence, provided, of course, they're not divided by 0. You can actually move limits of sequences inside of powers. So if I have a sequence and I raise that sequence to a power, then I can find the limit of the inside and then raise the result to the power. K is a positive real number. Now it works with negative real numbers as well, but you don't want to end up with like a division by 0 or something, so we'll tell you for positive real numbers. But in general, you can actually move limits inside of powers, which also include radicals, right? So the limit of the radical of a sequence is the radical of the limit of the sequence, etc. Yeah, so that's nice. Series, by the way, they're very picky. They don't work as nicely as limits. But limits do, they distribute across everything. You can factor out constants, they distribute across sums, products, divisions, they go inside of powers. Limits have always been nice, and just so you know, they remain to be nice with sequences. It is worth mentioning, though, that this only is true for convergent sequences. If you have a divergent sequence, there is no guarantee that any of these rules will work out. You could actually have, if one of these guys were allowed to diverge, it's possible that the limit does not disagree across the sum. It actually won't make sense, or it's possible that this breaks. These will hold true for convergent sequences, meaning the limit is actually going to give you a real number answer. Now, if that's true, this is what's going to happen. Something else you need to know, squeeze theorem still applies, and it applies almost exactly as you remember it from Calc 1. This is another thing to know. Now when we get to series, you'll notice that a lot of things that your intuition tell you should work don't work anymore, so I know you're rolling your eyes at me writing this down, but it's important for you to know which obvious things are going to work out in your favor and which obvious things are not going to work. So, turns out for limits of sequences, of convergent sequences, a lot of things that you know and love still remain true, including the squeeze theorem. So, if you have three sequences, an is less than or equal to bn is less than or equal to cn, and you know that the limit of an has to be a limit as you approach infinity equals L, and the limit of Cn equals L, then the limit of Bn equals L, right? So you can have this inequality, you can take the limits of all three parts. If both sides go to the same thing, then it squeezes the middle one to be that thing as well. So that's still true, that still works. L'Hopital's rule still works. So you're allowed to use that. Now L'Hopital's rule, it's very strange that L'Hopital's rule works because you're taking derivatives, and it's kind of weird because you just have isolated points. Technically you can't create a tangent line in a situation like that, but algebraically, calculation-wise, L'Hopital's rule is still going to work out. It's still going to give you a trend. So if you have the limit, and then of course it's always going to be n goes to infinity, so that's the only thing that's going to be different. So if you have a limit of sequences, an limit at infinity, and that approaches 0 over 0, or infinity over infinity, plus or minus, then you can calculate that limit as you approach infinity specifically, by computing the derivative of an and divided by the derivative of bn. And these two limits will always have the same answer provided the right limit exists. So, if you take derivatives of the top and bottom and you get some answer that makes sense, then you can assume that that answer transfers to the first original guy. So L'Hopital's rule still works, your squeeze theorem still works, all of the familiar limit properties still work. And that's all Calc 1 stuff, so I'm not really going to go over examples for that. Just know that whatever examples you did in Calc 1, they still apply here. With series, strange things are going to start happening, but with sequences, it's pretty familiar to how we dealt with limits in Calc 1. What else? There's a theorem that you should know. If the absolute value of the terms of a sequence approach 0, then the original sequence will approach 0. That's useful because there are some cases where you have things jumping up and down and you're not exactly sure how they're going to behave. A silly example, think of a sequence given by, say, -1 to the n over n, right? So that's just a list that's going to alternate. It's going to give you -1, then plus a half, then minus a third, then plus a fourth, then minus a fifth, etc. Right? So we have guys jumping up and down. Blah, 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 blah. You might say, what is that trend, right? They just keep jumping up and down. Is there no trend? It turns out this one does have a trend, and it actually does converge. What you can do is you can say, consider the absolute value of an. So that's going to give you 1 over n. And 1 over n converges to 0. This means the original sequence also converges to 0. You could actually see this by a picture. What's happening here is that you have a trend going towards 0 from both directions. So the guy starts out at -1, then plus a half, then minus a third, plus a fourth, minus a, and they keep hopping from the one trend line to the other. But essentially, from both sides, they're all squeezing into 0. So I can still determine that the limit approaches 0, even though there's kind of a jumping up and down that's happening. And absolute values is going to help out with that. Knowing when a sequence approaches 0 specifically is going to be very important in the future. So we're going to want to know when it approaches 0 in all cases. I think that's pretty much all I want to talk about for sequences. I feel like I'm forgetting something, but I can just remind you on Monday. We'll stop there for now. So on Monday we'll have a quiz. It will cover approximate integrals and their errors and just convergence of sequences.
And what?
Convergence of sequences. Yeah. So Simpsons Rule, Trapezoid Rule, know how to use them, know their formulas, know how to find errors for their formulas. I'm going to give you the formulas for the errors so you don't have to memorize that, but you do have to memorize the original formulas. I'll ask you about convergent sequences, and then we'll actually continue with series.